All right, so today I'm very excited to introduce Dr. Chengfei Hu. Dr. Hu completed his PhD in atmospheric sciences at The Ohio State University in 2021, and his dissertation is titled Deciphering the Deglacial Evolution of Water Isotope and Climate Across the Northern Hemisphere. Since graduating in 2021, he joined the University of Miami as a postdoctoral scholar in the Climate Research Group, where he still is, and he works on better understanding multidecadal variability in the North Atlantic. Dr. Hu has 24 publications and 4 extra that are on the way and have been submitted recently. He also has received many awards, and there's a very long and comprehensive list, so I'll name 2, which is, he received this twice, the E. Willard and Ruby S. Miller Fellowship at The Ohio State University in 2019 and 2021. And The Ohio State University very much advertises this. This is the highest honor a graduate student can receive at his university. Outside of the Rosenstiel School, Chengfei can be found hiking, cooking, and building mechanical keyboards. So if everyone could join me in welcoming him.
Thank you, James. Thanks for everyone coming here today. So today I'm going to present a recent breakthrough on the driver of the Atlantic Multidecadal Variability. So this work is a collaboration with Amy, Mark, and other like Lisa and other alumni like Sydney, Jeremy, and Tyler. So basically my conclusion is just the title. The recent tropical Atlantic multidecadal climate variability is driven by external forcings. So I will going to cut this presentation into 3 sections. So after each section, I will stop for several minutes. So if you have any questions, so just ask during the brief, and then I will keep going on. So what I show here are 2 family portraits. So they are generated by AI. And in the first one, so we see that the dad is the AMOC, and the mommy is the AMV, and they have 2 kids. One is the Northern Hurricane, and another one is Sahel rainfall. And probably this picture is the most believed one in what happened in the tropical Atlantic. And in the second one, so the data is replaced by the NAO or external forcing. So today our task is to find out which one is more like the real world. So basically we have 2 questions here. So who is whose partner and who are whose children? So we will use some genetic tests to identify the true family. And the genetic test here is the large ensemble simulation provided by the CMIP6 archive. So, but before doing so, let's first recap some background of this story. So what I show here, it is Atlantic Multidecadal Variability, the AMV. So basically it is the sea surface temperature fluctuations over the multidecadal time scale. So on the left, what I show here, it is a spatial map of the positive AMV. So during the positive of AMV, we see there is a dipole response in the whole Atlantic. And in the North Atlantic, we see, so it is a strong warming, and it also has kind of a hostile pattern. And on the right, what we see here is the AMV index. And this index, we can see it goes ups and downs and has a cycle of several decades. So basically this is AMV. And the decadal variability is actually not just in the sea surface temperature, but also in other like climate variables. What I show here, so first it is the rainfall in the Florida. We see that it has very distinctive high and low arrow, and this corresponds to the phase of the AMV, basically the temperature in the North Atlantic. And another one is the hurricane activities in the east coast of the United States. What I show here, it is provided by NOAA, the Atlantic Cumulative Cyclonic Energy. So basically you can think this is a proxy for the hurricane activities. And again, here we see it has very distinctive high activity and low activity arrow, and this arrow corresponds to the phase of the AMV. And not just in the east coast, but also like remotely in the North Africa. So what I show here, it is a rainfall of the Africa in these Sahel regions, and it is also correlates well with the sea surface temperature change in the North Atlantic. So we see here, so the AMV is not just in the SST, but also in other climate variables. And we argue so this is a tightly coupled tropical Atlantic multidecadal climate variability rather than the AMV, which stress on the sea surface temperature. And then the cause of this AMCV is actually very controversial. So usually it falls into two categories. The first one argues that it's driven by internal dynamics like the AMOC or the NAO, because the AMOC is large-scale ocean circulations that transport energy from the Southern Hemisphere to the Northern Hemisphere. So any change in the AMOC would cause this dipole response in the Atlantic, and therefore naturally it leads to the AMV change. And another one is for the ANO. It is NAO, so it is the circulation change in the high latitude of the North Atlantic, and it will affect the AMOCs and other processes that lead to the AMV response. And another category falls into the, they call it external forcing. So we know, so there is a lot of external forcings like the anthropogenic aerosols or volcanic eruptions. When we include these in the simulation, so they all produce the so-called AMV-like patterns in the Atlantic. But both arguments actually have pros and cons. So in the next few slides, I will try to provide 3 representative examples. And in each example, you will see how could they explain the observation, but they also fill some other aspects of the observation. So the first one is from a PI control run. So in PI control simulation, so the forcing is fixed. So any change is because of the internal variability. So in this simulation, so what I provide here, so the AMOC change leads to this dipole response in the Atlantic. As we see here, there is cooling in the South Atlantic and a warming in the North Atlantic. And this warming has kind of a horseshoe pattern. So it is quite similar to what we observed in the real world. So this seems to suggest that this AMV is because of the AMOC change, because of the internal variability. And associated with the warming in the North Atlantic, we can see so the rainfall in the Sahel region also increasing. So this is also consistent with observation. So combine these together, it seems that the real world AMCV is because of the AMOC. But the problem appears when we try to quantify the covariability in the system. For example, if we calculate the correlation between the AMV and the Sahel rainfall, so it is just a 0.2 in the model. But in the real world, what happened is their correlation is about 0.8. So it seems that there is a large gap here. And if we further calculate the correlation between the AMV and the vertical wind shear, so vertical wind shear is a proxy for the hurricane activities. You can think about this. And we see that in the model, their correlation is around 0.4 or 0.5, depends on what kind of model you are using. But again, in the observation, we observe that their correlation is about 0.8. So it seems here is that the internal variability shows some covariabilities in this system, but it is just not close to those we found in the observation. So the second example is associated with the external forcing, and the external forcing could improve the covariability in the system, but it only shows in some particular models, in particular in the mostly they are found in these meta office models. So what I show here on the left, it is the observation. On the top panel, it is the hurricane frequencies in the Atlantic, while in the bottom, it is the AMV. So you can see they are highly correlated. And when we add external forcings like anthropogenic aerosols into the model, so we can reproduce this tight covariability in the Atlantic AMV and the hurricanes. So it seems that the external forcing could explain this covariability. But this has been challenged, so the aerosol forcing, it is probably too large in these models. So then it seems it's not so trustful here. And the last example, what I want to share is that both external forcing and internal variability cannot explain the AMCV tight connection. What I show here, it is a regression of the geopotential height at 500 millibar onto the AMV. So we see here in the observation, so there is a clear Rosenstiel wave tight connection here. So it will affect the weather in the mid latitudes. And we could also calculate this in the model simulations. what I show here, it is the ensemble mean for the CESM1 large ensemble. So the ensemble mean is a false response. So what do we see? Well, we calculate this regression. So the teleconnection pattern is actually quite different from the real world. So it seems like the external forcing fails to explain this teleconnection. And this is another example. So this is from the CMIP6 simulation. So in this example, so they calculate this teleconnection associated with AMV in both PI control runs. So in PI control run, it is purely because of internal variability. While in 20th century historical simulation, so it is because of external forcing. We can see compare these two with the observation, we can see they are also quite different. So to summarize here is that we found both internal variability and external forcing can explain part of the real world, but they don't provide a complete explanation for the real world. So then this comes to our first question. So what is the cause of the ANCV? And the second one is that what I show here is three different definitions of the AMV index. Actually, the definition of the AMV index is kind of very different. So the first one comes from the first paper of the AMV. So they basically detrain the Atlantic SST and do a low pass filter to get a multidecadal variability. And the second one, so because it is a linear detraining, so you can imagine the global warming is definitely not linear. So in this index, there is some global warming signal inside. Then people argue, so because AMV is an internal variability, so this index includes some like global warming signals there. So then comes to the second index. In this index, so it is a difference between the North Atlantic SST and the global mean SST. So the global mean SST is largely false because it is global mean. So then we just remove the false response, like the global mean SST from the North Atlantic SST. What left is like internal variability. The last one is kind of built on the second one, is that it's a regress on the North Atlantic SST onto this global mean SST. So in this way, it will remove the false response even more than the second index. So what left is the pure internal variability of the AMV. So combine all these together, we can see they are quite similar, but they are also quite different. So it seems like, so this comes to our second question, can we define an AMV index? So in this AMV index, we could naturally remove the global warming signal, but also includes like the anthropogenic aerosol or volcanic eruptions. So with these two questions keeping in mind, so we try to use the CMIP6 model simulations to answer these two questions. So we first use historic simulations from 46 models. So in total, we have over 400 ensemble members. Therefore, the ensemble mean can largely remove the internal variability and isolate the external force response. And we also use PI control simulations from 31 models. We are trying to use the PI control run to quantify the role of internal variability. And we also use the single forcing runs from a DA-MIP to quantify the role of the external forcing. In DA-MIP, it has the greenhouse gas only run, the anthropogenic aerosol run, and the natural forcing run. So each single forcing has roughly 70 to 100 members. So for observation, we use a list of observations, but the statistics between them since 1950 are quite close. And the study period for this is from 1950 to 2014. So during this period, we have like reliable observations for the hurricanes and the Sahel rainfall. Because when we focus on the observations before 1950, they had large spread there. And all data here is from the June to October because we most focus on the summer impacts rather than other seasons. So we see here is the result. What I showed here, it is the detrended, low-pass filtered, and normalized time series for the observation and the CMIP6 ensemble mean. So for the CMIP6 ensemble mean, so basically it is a force response. And in observation, it includes both force response and internal variability. So from top to the bottom, we see the index for the AMV, Sahel rainfall, and vertical wind shear. We see all the model simulation and observation, they align together. So the correlation between the modeled AMV, Sahel rainfall, and vertical wind shear, actually they are highly correlated. The correlation is about 0.9. So based on this correlation, so more than 80% of the variance in the real world is of the real world AMCV is driven by external forcing, because based on the linear regression, so the square of the correlation is a fraction of the force response explained by the CMIP6 ensemble mean in the observation. So based on this plot, it seems to suggest that the real world is indeed driven by external forcing, but it doesn't rule out the possibilities that in the real world, the internal variability and external forcing, they overlaps each other. Therefore, the internal variability may also have a very important role in the real world AMCV. So then we try to test the idea. So if the internal variability alone could produce a real world AMCV. But remember, if the observed tropical AMCV could arise due to internal variability alone, then one important thing is the statistics of this AMCV system must be similar in both model and observations. So one statistics, what I focus here is this covariability. Basically, it is the correlation between AMV and the Sahel rainfall, or the correlation between AMV and the vertical wind shear. So we calculate these two correlations for the observation. So basically, it is a red star here. So we see this correlation for the observation are about 0.8, and this is consistent with previous studies. And then we calculate these correlations for the ensemble members, but before the calculation, we remove the force response from each ensemble member during the historical simulation. So we denote this as correlation without forcing. And then we calculate the correlations. So the result is the shading here. Basically, it is a 2D distribution, and the pixel is the number of realizations that has this correlation. So what we observe here is quite clear. So the observation is at the end, at the tail of this distribution, and 0 out of 400 in the historical run with the forcing removed could have a correlation higher than the observation. So this suggests that the internal variability alone cannot produce this real-world AMCV. And actually, we found that in the model, this internal variability, the correlation between the AMV and its impacts for the internal variability has a very large spread. And this is expected because, think about this, if there is no external forcing or the forcing is fixed in the simulation, so then the correlation between the AMV and its impacts could be easily interrupted or intensified by other processes, for example, the aerosol and the PDO. So this is why sometimes we observe they have very high correlation, but sometimes they have very low correlation. And overall, the mean of this cluster is the green star here. We denote is the mean of the ensemble. We see it produces some correlations, but it is very far away from the observation. And the correlation associated with this green star, the MOE, we can see their values are quite consistent with previous studies. So from this point of view, we see that the internal variability alone cannot produce this real-world AMCV. And we also checked this in PI control run. So in PI control run, there is no external forcing. Everything is fixed, and change is because of the internal variability. And we repeated this process for the 31 climate models, and for each model we just subset a time series that the same length as in the observation, and then repeat the calculation for 100 times. So in total we have 3100 realizations here, and we can see here compare the top and bottom panel, we see the distribution, the shading are quite similar, and the mean of the shading are also quite similar, and they are all far away from observation. And the statistics is listed on the right bottom. So less than 2% in PI control runs has one correlation value higher than observation, and only one in these 3,100 realizations in PI control runs has both correlation values higher than the observation. So this again confirms that the internal variability alone cannot produce this real-world AMCV.
Do you remember what model that was in? Just curious. Like,
oh, you mean the 2% and the one?
The one that had the correlations higher than observation.
I didn't check that.
Okay.
Yeah. So okay, well, so we then calculate their correlation with the forcing in single ensemble members. So in this way, once we calculate this correlation, we see this cluster is still has a large spread, and the observation is at the tail of this distribution. But if we calculate the correlation in the force response, the ensemble mean of the CMIP6, so we see that basically this is the blue star here. We see the blue star and the red star, they are quite close. So this suggests that this high covariability in the real world post 1950 AMCV only emerged in this force response. In single members, they cannot produce this high covariability in the AMCV. So if these evidence still cannot convince you that the real world AMCV is driven by external forcing, then I will show next piece of evidence, and this is independent. What I show here is the AMCV related tight connection. Recall that at the beginning I showed both internal variability and external forcing, they failed to explain this tight connection. So we again analyze the tight connection in the CMIP6 ensemble mean, the force response. And on the left, it is for the observation. So from the top to the bottom, it is the circulation at the high level of the atmosphere, in the lower level of the atmosphere, and the surface rainfall. What we can see here is that they are quite consistent. It is much better than in previous studies. And because of the circulation change, we can see there is an increase in the Sahel rainfall, and also in the South Asia, in the North Asia, and they all reproduce in the CMIP6 ensemble mean. So this again confirms that the covariability in the AMCV and the AMCV teleconnections, they are all driven by external forcings. So a short summary here is that the internal variability is very unlikely to lead to the real-world AMCV since 1950, and the real-world AMCV is mostly forced. And this tight connection is also forced. So I'll stop here for a little bit, so if you have any questions, just feel free to ask.
Yeah, clarifying question. The MOE is internal variability only, no aerosols of any kind?
Yes, MOE is actually, it includes internal variability as well as external forcing. It is the mean of this cluster. Basically, we collect all the correlation values and do the average. So in this way, if the correlation with forcing, then the MOE is the total correlation. It includes the external forcing and the internal variability. But if, for example, in this one, so without the forcing, then it is totally because of the internal variability.
But they're still CMIP6 class models.
Yes, there are CMIP6 models.
We have a question in Zoom.
Mm-hmm.
Okay. Can you switch your microphone on?
Okay.
No, the Zoom person.
Yeah, this is Paul Gino from GFDM. And I was wondering about internal variability. If you include dust from Sahel and Sahara, which will affect, for example, the tropical Atlantic, it will change your internal variability, correct? Because all these CMIP6 models, it has been shown, are unable to reproduce the strong variability observed by Joe Prospero, who is most likely in the room, at Barbados. So I wonder if you include dust, if your conclusion will stay the same in terms of internal variability. Thank you.
So I think in CMIP6 models, so some of models definitely have the dust inside it because it is a type of aerosol. Some of them may not have. So I don't know if I separate the CMIP6 models into those have dust and those don't have dust, what it would look like. So I think this is definitely an interesting topic to explore in the future.
But no, what I am saying is that the CMIP6 model with dust are unable to reproduce the factor 4 or 3 to 4 increase during the sand drought. So even if you take only CMIP6 model with dust, you will fail.
Could you repeat the question again?
So the CMIP6 model are unable to reproduce the time series observed at Barbados with an increase of a factor 3 to 4 of dust concentration, so affecting SST. And so I was wondering if you have a model or you add this forcing by dust, you will be able to your internal variability will change, will be more close to the observation.
Oh, I see. So in this way, you are arguing that the dust is also driven by internal variability, then it affects the AMV and therefore these tropical impacts. It is possible, I would say it is possible, but I don't know how important it is because there is so many factors could attribute to these tropical impacts and the AMV. Definitely this one would help, but I'm not sure if I'm not sure so how CMIP6 models kind of take care of these dust emissions. Like I would say some of them definitely have these, therefore. But anyways, I think for historical runs, so they will have this kind of dust forcings, but still we didn't see that the internal variability could produce this observation.
Well, we have another comment from the other Zoom participant.
Yes, can you hear me?
Yep.
Yes, I'm wondering about these, when you look at, this is Tom Knudsen from GFDL, when you're testing these internal variability, so you take internal, some segment from control run, which would have sort of randomly phased internal variability, and then you're comparing all these randomly phased segments from control runs to the observation. So you expect some of them to even be negatively correlated. It's just that kind of occasionally you have one that just due to random chance, it's kind of well phased with the observation. Is that the case? So that really it's not, you're not saying it's that, you're not saying it's impossible that internal variability could get pretty close. A lot of these internal variability episodes are just randomly phased anyway, so you would expect them to have low correlation. Is that the right interpretation?
So I think so when we compare the internal variability with the observation, so because for the time series, so for example the AMV, they can change in anyway for internal variability. So when we compare the correlation between the time series of the AMV between ensemble member and the observation, so this is unfair because it will automatically, because the internal variability has so many ways. When I compare the covariability, so this covariability is the feature or statistics of this system. If the real world could be reproduced by the internal variability, then I would expect the statistics in the internal variability has to be close to the observations. So for example, if this cluster, like in the top panel, if this cluster is around the red star, around the observation, then I would accept the hypothesis that the real world could be reproduced by the internal variability. Right now, it seems like the shading here, basically the model internal variability, is totally different from the real world. They are two separate systems. So in this way, I reject this hypothesis that the internal variability could produce the real world AMCV.
I guess my interpretation of it would be that you have all these randomly phased realizations of internal variability from control runs, which you don't really expect to be correlated with observations, but just by chance, some of them get close. And so the fact that some of them get close just due to random chance tells you it's possible that internal variability could be doing it, but that you're just sampling. The reason why you're getting all these low correlation values is just because of random phasing. It's just experimental design.
So I think first is that for correlation, it doesn't matter with phasing of the time series because it is correlation between the two metrics. And the second, I do agree with you that the internal variability is possible to produce the real-world AMCV. But the possibility based on the distribution here, it seems it is very low. And the alternative explanation is that the real world could be easily produced by the force response.
So I'm really enjoying your talk, but I really struggle with this idea that you can ignore dust, because we know that the 80s, a time period with little Sahel rainfall, was also a very dusty time period. When you get dust over the Atlantic, there's also a feedback with the clouds there that you get more clouds, so that's going to cool the SSTs even more. So you're going to get a stronger, something stronger in your observations than you would get in a model that excludes the dust. And it's not really fair to call that the dust an external forcing agent, which I think is what you're doing.
We call dust probably like the natural forcing.
Yeah. I really think it's part of.
Yeah, absolutely. I think I will mention it at the end of this talk, because I will mention a big program in the climate models, and include the dust feedback into the AMCV system definitely helps to improve the program in the climate models.
Yeah. I'm not surprised.
So next, what I'm going to do is I'm going to explain the mechanism behind this AMCV. So we argue that this AMCV is because of the geotype response. What I show here at the top is a geo model. So when we have asymmetric heating, like heating in the North Tropical Atlantic and cooling in the South Tropical Atlantic. So this is like in the positive phase of the AMV. So it will induce a baroclinic mode in the North Tropical Atlantic. So in the low level of the atmosphere, it will lead to a cyclonic response circulation, and in the high level of the atmosphere, it would be an anticyclonic response. And based on the geo model, we do find that in the observation and the CMIP6 ensemble mean, so we see that in the 850, we see there is a cyclonic response in the lower of the atmosphere. So the westerly anomaly transports the water vapor to the North Africa, therefore lead to the rainfall there. And at the top of the atmosphere, we see there is an anticyclonic response, and the easterly wind anomaly so prevails in the tropical Atlantic. And together with the westerly anomaly in the low level of the atmosphere, they perturb the vertical wind shear, therefore affects the North Atlantic hurricanes. So it seems like the Sahel rainfall and the North Atlantic hurricanes, they are both driven by this tropical Atlantic sea surface temperature contrast. So based on the mechanism there, so we propose that this tropical Atlantic SST contrast, we call it AMM. So the AMM is the Atlantic meridional mode. So it is very similar to the definition for the tropical Atlantic SST contrast. We propose that AMM could be an index of the AMV, at least for the tropical impacts. And if we define the AMV index using the AMM, it actually has several advantages, both statistically and physically. The first one is the statistically. So first is that the AMM naturally removes the global warming. So what I show here is the non-detrended, the 10-year low-pass filtered AMM vertical wind shear and the Sahel rainfall for the whole past century. And you can see here, they don't see clear trends. And after 1950, you can see they are highly correlated between the AMM, vertical wind shear, and the Sahel rainfall. So the physics behind this is because the global warming, the CO2-induced warming is largely uniform in the tropical Atlantic. So as a result, the north and south difference remove this global warming and provides us a time series. And the second advantage appears when we try to quantify the role of different forcings in the tropical AMCV. So I'll skip the technical details how we do this. The result is like this. For Sahel rainfall, hurricanes, and AMM, we can see they are mostly driven by the anthropogenic aerosols and natural forcings. The greenhouse gas actually plays a minimum role. The physics is I explained before. Both anthropogenic aerosols and natural forcings, they could lead to a sea surface temperature gradient in the tropical Atlantic, therefore induce a gill-type response. So as a result, the AMM affects the Sahel rainfall and vertical wind shear. But for greenhouse gas, usually it is uniform warming, therefore it cannot affect these two tropical impacts. And the further is, if we focus on the AMV is defined the average of the North Atlantic sea surface temperature. So we can see the greenhouse gas do play some role here. I think this is not surprising because it is just North Atlantic and it is linearly trended, so it do have some greenhouse gas roles there. So from this point, so we can see that this tropical AMCV is mostly driven by the anthropogenic aerosols and natural forcings, but AMV is additionally impacted by global greenhouse gas because of the definition of the AMV index. So next, you may be interested in that how is the AMOC? Actually, what we found in the CMIP6, the ensemble mean of the CMIP6 AMOC time series is out of phase with the AMV in the real world as well as in the model. So the physics behind this is like the AMOC probably is a negative feedback to the AMV. When we have cooling, for example, in the 1970s to 1990s, so the cooling in the subpolar North Atlantic will increase the mixing in the high latitudes, like those deep mixing regions. Therefore, it will increase the intensity of the AMOC. Then the increased AMOC will try to transport more energy to the North Atlantic, therefore try to dampen the AMV response. So the next is how about the pre-1950 AMCV? So we again do this distribution analysis, and we found that for pre-1950 AMCV, actually the observation and the MOE, basically the green star here, they are very close. So from this point of view, it seems to suggest that the pre-1950 AMCV is likely driven by internal variability. I say likely because we have several different products for observation. So we are able to calculate the correlation for different combinations. And this is the small purple star here. So we can see that actually it varies a lot. So it suggests that in observation, it has a lot of uncertainty there. So based on the uncertainty of the observation, here I conclude that the pre-1950 AMCV is likely driven by internal variability. So a short summary here is that we found this tropical AMCV is mostly driven by the natural forcings and anthropogenic aerosols since 1950. And the AMM could be an index for the AMV, in particular for these tropical impacts, because we don't need any trending. And the implication here is we found the hurricanes, the Sahel rainfall, they are far more predictable than previous sort in recent decades. And pre-1950 is likely driven by internal variability, but we have to be careful about the uncertainties in the observations. So this is the second section. So if any questions here. Okay, so now let's return back to this family portrait. So at the beginning, I showed two family portraits. In the first one, The AMOC and AMV are coupled, and in the second one, the NAO and the external forcing and AMV are coupled. Here, what I show here is right now, I think both of them are not that correct. After we carefully checked the tropical AMCD, we found it is because of the aerosol and the AMM. They produce the Sahel rainfall and the North Atlantic hurricanes. So this after this genetic test, we found the family in the tropical Atlantic in the real world is actually on the right-hand side. So model is not perfect. Actually, it has some problems here. So remember at the beginning I said I detrended the time series and I normalized them. So then what if I don't detrend and not normalize them? What would happen? So the first thing I want to show here is that so on the left-hand side, it's detrended and normalized. So they are all consistent between model and observation. So on the right-hand side, I didn't detrend the model, but normalized it. So you can see now the model and observation are quite different. For the North Atlantic sea surface temperature, it seems like model is doing reasonably well. But for the Sahel rainfall and vertical wind shear, you can see the blue and the red, they are quite different. The model, the Sahel rainfall and the vertical wind shear actually follows the North Atlantic sea surface temperature. Overall, it has an increasing trend. But in the real world, the Sahel rainfall and vertical wind shear, they are quite different from the North Atlantic sea surface temperature. And the difference between the model and observation is this gray curve here. We see clearly there is an increasing trend in the Sahel rainfall and a decreasing trend in the vertical wind shear. And the difference is largely linear. And this spurious trend is also obvious kind of in the North Atlantic SST as well. And we argue this spurious trend is because of the model data difference in the inter-hemispheric sea surface temperature contrast. What I show here, it is a sea surface trend difference between the ensemble mean of CMIP6 and the observation since 1950. So we see clearly in the Northern Hemisphere ocean, the model warms faster than the observation. But in the Southern Hemisphere ocean, so the model warms slower. So this actually creates an energy imbalance between these two hemispheres. So on the right, what I show here is we quantify this inter-hemispheric sea surface temperature contrast. Again, we see in the observation, it is overall, it doesn't have any trend, but in the model simulation, it has an increasing trend. And this is very similar to what we observed in the Sahel rainfall, in the vertical wind shear, or in the North Atlantic SST. And the model data difference, what we see here is this gray curve. It also has a largely linear increasing trend. Physically, it is because when we have an energy imbalance between these two hemispheres, so it will push the ITCZ northward, therefore lead to the spurious trend in the Sahel rainfall and also in the vertical wind shear in the tropical Atlantic. Therefore, we see the spurious trend bias in the CMIP6 model simulations. We do have to remove this spurious trend and try to detect the multidecadal variability in the tropical Atlantic. And we also calculate the trend for the Indo-Hemisphere sea surface temperature contrast. What we observe here, like the observation, is again at the tail of this distribution for CMIP6. So it seems to suggest that internal variability is unlikely to explain this systematic bias in this inter-hemispheric sea surface temperature contrast. And also, for the greenhouse gas, it is close to the CMIP6 simulation, and for the anthropogenic aerosols and natural forcings, they are kind of close to zero. So the bias may relate to the greenhouse gas because it is overall it leads to so much warming in the Northern Hemisphere. And the second may be because of the underestimation of the aerosol impact, because the aerosol could form a gradient between two hemispheres, but it seems like the ensemble mean of the aerosol is kind of close to zero. Therefore, it is not enough to cancel the warming due to the greenhouse gas. But this is a remaining question, so we are going to explore in the future. So, okay, the second problem is, I said I normalize. What if I don't normalize it? Here, on the right, I detrend the time series, but not normalize the time series from the observation and from models. So then you can see that the response of this force response in the model actually is quite different from the observation. We see for A and V, probably they are kind of similar, but for the Sahel rainfall and vertical wind shear, actually there is almost zero response in the force response in the CMIP6 simulations. It is quite different from what we have on the left-hand side. But if we calculate the correlation between this blue curve and the red curve in the right-hand panel, then their correlation is actually very high. The model's force response do produce all the wiggles like what happened, for example, in the left bottom panel for the vertical wind shear. All the wiggles are produced by the CMIP6 force response. So this seems like the external force response in CMIP6 models is way off. And this is actually the signal-to-noise paradox in climate models. So when I say signal, it is a force response, and the noise, it is internal variability. So the signal-to-noise is basically the force versus the internal variability. What we see here, I calculate the signal-to-noise ratio for different climate modes and also for global mean sea surface temperature and ENSO. What do we see here? First, for ENSO, that we know it is internal, it is pure internal variability. So what we observe in the observation and in the model, their signal-to-noise ratio is 0. This totally makes sense because there is no force response in ENSO. Then for the global mean surface temperature, sea surface temperature, we see in both model and observations, they have a high signal-to-noise ratio because we know the global mean surface temperature is largely forced. Therefore, it also makes sense. But when we take a look at these different climate modes like AMV, vertical wind shear, Sahel rainfall, AMM, NAO, or PDO, we see in the observations, they all have a very high signal-to-noise ratio. That means in the observation, these modes are actually driven by external forcing. But what we observe in the CMIP6 models, we see these signal-to-noise ratio is so low. So that means in CMIP6 models, these variability are mostly dominated by internal variability. The force response is so small compared to the internal variabilities. So finally, the take-home message here is that we found the tropical Atlantic AMCV is mostly driven by the natural forcing and the anthropogenic aerosols. But we have two problems left. The first is what I call this model data difference in this inter-hemispheric sea surface temperature contrast. And the second is why the signal-to-noise ratio is so low in the model. So yeah, I'll stop here. Thanks if you have any questions.
Yeah, I was just wondering, is the signal-to-noise ratio also so low in previous CMIP runs? Or is it improving? Like you would think that with time that the newer ones would get better to signal this, and it's improving. Yeah.
This is a good question. So we hypothesize so it should increase the signal-to-noise ratio in CMIP6 models compared to the previous ones, but we didn't see that. One example is in CMIP6 models. So all these models have kind of indirect aerosol effects, but in previous ones not all of them have this one. Then when we subset the CMIP6 models into the high aerosol forcing and the low aerosol forcing, basically based on the aerosol cloud interaction, we observe that the signal-to-noise ratio between these two groups are actually very similar. So from this point of view, I would say there is no improvement in current CMIP6 models.
Follow-on question, if that works. Then I guess with this specific area that you're looking at with the North Atlantic and everything, have you done similar studies on previous runs or groups of CMIP models to see if the results are the same or if it shows any difference? If the signal-to-noise ratio isn't improving, but if the results are still the same or if it's different? Yeah,
excellent question. So I think the results are pretty similar. So why we could find out this fully external force AMCV is we cut it at 9050 because after World War II, the aerosol forcing and greenhouse gases rarely ramp up. But before that, it seems like the anthropogenic forcing is kind of small. So it is also, I think it is also intuitive. Before that, it is mostly driven by internal variability. If we focus on the whole past century, then the problem is that they just cancel each other, then lead to like I showed here, the correlation would be kind of in between low and high. So then we don't know what it is. So yeah, thank you.
Cool, thanks.
I just want to go back to the dust story. Do you think, let's say the idea from the question online was that dust feedbacks in climate models are too weak. Do you think that's the answer to the signal to noise ratio problem?
This is a good question. I would say this definitely could be one of the answers. Like what I found in these CMIP6 models for those historical simulations. So if the model have a high resolution, like the EC Earth, so they have really high resolution, and it really produce a better result than other low resolution models. So this is one possibility. Another possibility is the role of the ocean. Like in our slab ocean models, we observe the signal to noise ratio is really high compared to these 40 coupled models. So it seems like something is problematic in LC coupling, therefore affects the signal to noise ratio in these atmospheres. But still, definitely there is some problem in atmosphere model as well, because even if we have the perfect sea surface temperature, like if we have the observed sea surface temperature, try to prescribe it at the boundary condition in the AGCM, we still see that the time evolution of the, for example, Sahel rainfall, they definitely correlate well with the observation. But the problem is the magnitude is still too small compared to observation. So it seems like all these components have some problems there. So.
And what about dust?
Dust definitely could help. Yeah, true. Dust could definitely help to amplify this signal to noise ratio in the tropical Atlantic, therefore fast. But still, it cannot explain like the NAO, like the PDO. So yeah. So I would say this is one possibility, but there is so many other possibilities there as well.
Is your ocean just the sea surface temperature, or do you have structure in the ocean?
It is a fully dynamic ocean. It has 3D dynamics there, so it is fully covered models here.
Thank you.
What happens next for Sahel rainfall? If there's not a role for greenhouse gas forcing, can you predict anything about the future?
I would say if we keep decreasing the aerosol emissions in the North Atlantic and the Europe, so then in the next few decades, so it would still increasing. But for the future, then this is a different problem, because here what I'm focusing on is multidecadal variability. So it is on decadal scale, but the future is kind of a long-term, it is a trend. So like I showed here, so the interhemispheric sea surface temperature contrast is not correct in the model simulation. So can we trust those predictions in the future for the tropical rainfalls, or like we do have to fix this first, then to do the prediction, so what it would be look like. But yeah, so.
So you're saying you can't predict it?
Yeah. On multi-decadal time scale, I would say it would increase, but for the long-term trend, I don't know. Yeah, this is definitely a problem there.
And so you think the increase is from continued aerosol emission?
Yes. And also, like, if there is like volcanic eruption, so it can totally change the picture there. So yeah, this is an unpredictable thing.
We have a new comment from Mr. Ginou in Zoom.
Yeah, this is Paul Ginou. So I did simulate with a fully coupled model with the Vecchi, who is now in Princeton, and a student, Jeffrey Strong. The influence of dust following this increase related to the Sahel drought. And we did find a strong effect on sea surface temperature, creating this asymmetry between the North and South Atlantic. And we were able to reproduce the hurricanes number and intensity much better by including dust in a coupled climate model. Because CMIP6 totally failed. It's totally flat. There is no variability decadal variability of dust in this model. That's it.
Okay.
Thank you.
Good to know. Good to know. Thanks. Yeah. Then my follow-up question is the dust force or because of internal variability? So this is I don't know. Yeah, I would say this is definitely a very interesting topic to investigate in the future.
It's so problematic that the dust modeler some are suggesting to force this emission. But myself, I do believe it's because of the link, the relation with vegetation. So you have precipitation, increased vegetation, decreasing the dust source and emission, and so it's related by vegetation. So we need the dust modeler to link dust emission with vegetation, and we actually fail that link.
Thank you.
Sounds like the mid-Holocene problem too.
Yeah, like Green Sahara. Yeah.
But Chengfei, didn't you say that some models have dust and others don't? Like, and there's a MIP out there, right, that looks at different aerosol impacts. Like, couldn't you kind of answer some of these questions with the data sets you're already working with, basically?
I think so, but I don't know. What I'm relying on is the CMIP. So it is just a single forcing runs for greenhouse gas, anthropogenic aerosol, natural forcing, and ozone. So I would say in natural forcing probably there is some dust forcing there, but I'm not familiar with those forcings and the simulations, how they incorporate the dust or the volcanic eruptions in the model. So to me, I'm just a data user. Sorry. Yeah.
Yeah, there's a new trend in massive sargassum sea, sargassum weed growth in the tropical Atlantic, and so there's some shift in a nutrient source most likely. And do you think that may be carried by the aerosols or other things that get rained out into the ocean? And do you have an idea of what the upstream source might be?
This is a good question. I do not have a good answer probably. So if anyone here have better thoughts, so may just take.
I mean, it could be riverine and then transported by the equatorial current system as well. I mean, that's another possibility.
Oh yeah, and also like the sea salts, aerosols, like the bubbles from the sea surface temperatures, they all has kind of aerosol effect there. They also could affect the sea surface temperature. But yeah, I think this is a very interesting topic, and it's worth to take a look at in the future. Thank you.
Okay, if there are no further questions, thank you again for the nice presentation. Thank you all for coming. There will be no seminar on Friday because we have the faculty meeting. But next Wednesday we have something very interesting with two guests from Finland. Again in this room. I hope you will all come back.